here it's in its alternative state. Now, in this sort of system, it is possible to get back from there to there, but it can cost you an awful lot in terms of effort and change. I don't know if you're familiar with rangeland management and the interaction between livestock and fire and grass and trees. You can turn a rangeland which is productive for cattle into something which would only produce goats and cows. And it's very difficult to get it back once you've flipped it from that sort of open savanna with lots of grass to a tree or shrub savanna with almost no grass. But it's technically it's possible. There are other situations such as intensively irrigated soils that become salinized. The salt comes up through the water table, so it rises to the surface. You can't grow crops there anymore. And because of the changes to the physical and chemical properties of the soil, you can't get the salt out. So a system like that is essentially changed forever. Certainly in many human lifetimes, there won't be anything to do with it. It has to go through landscape kinds of processes to get rid of the soil.
Any other questions? Looks good.
All right. So we'll just have a look at these stable states and thresholds a little bit more. This is an example from Zimbabwe where I spent a lot of my life as a practitioner. And it's essentially that situation that I've just described. Very high animal density, grass cover here on the left. But if you maintain a high animal density, you eventually end up with this situation where you don't have much grass and you can't keep any livestock. And you get this positive feedback within the soil system which maintains it in that bare state. Rainfall can't penetrate the way it should do. So the opportunities for grass seeds to establish themselves and take just aren't there. And because there's vacant soil there, then the shrubs tend to invade the vacant spaces and take over and shade out the grass. But if you clear it mechanically, then it'll go back. And then this is another example of how it might go back. And this is still some experimental work based on changing the relationship between the livestock and the soil based on the amount of time that they actually spend grazing in the area. And the experimental results so far say that you can turn the system back by changing the grazing duration from long to very short, very intense. So when there's a little bit of annual grass in a system like this in the rainy season, you pack it with livestock. They break up the soil, they defecate, they urinate, bringing in lots of nutrients, and that creates conditions where grass can come back. This is an example from, I think it's from Papua New Guinea. This is a lake that's covered with a water weed known as Salvinia. It locks up all the nutrients in the lake, it stops the life from getting into the lake. It's highly undesirable. It's actually a Canadian invasion from South America. And they use this little beast here to get rid of the Salvinia and turn it back to a lake. One of the things that they had to do, which was counterintuitive, was that they had to put more nutrient into the water to create enough nitrogen in the system to make this palatable to these guys. Putting nutrients into water is generally regarded as not a good thing to do, but in this case they had to do it because the nutrients, the few nutrients that they were locked up in the plant, there wasn't enough to make them really attractive to the weevils, so they had to make the Salvinia super tasty for weevils by giving them more nitrogen, and then the weevils clean them up. Right, this is a little graph showing me these different kinds of alternate stable states. So this one here is the one that we looked at earlier. It's possible to get it back from the one system to the other. And this is one where irreversible change, where essentially irreversible changes has occurred. And understanding these alternate stable states and the feedbacks that maintain one condition or another is really the essence of managing resilience. So you can put all of that into a model. These Baldwin basins here represent the Panaky and the Baldwin basin model all in one picture. And then these are the dimensions of the basin. And this is the position of the ball in relation to the edge of the basin. So this is the critical thing, the precariousness, and how close the system is to the threshold. And you can monitor that, and you can measure that for a defined system. It's not something that you can invent a priori and say, oh, we need a bunch of indicators. You've actually got to understand the system, develop a model of the system and how you think it works. And then based on whatever theory you have, whatever local knowledge you have, you can come up with a measure of this. And then you manage the system adaptively to determine whether that modeled estimate of precariousness is correct, to see how it changes as you manipulate the system. And you can do that in two ways. One is through passive adaptive management, which is you go in and you do whatever it is you want to do, and you monitor the outcome. The other thing is you can take small parts of the system and experiment with it deliberately to see how far you can push it before it flips into an alternate state. Because it's understanding this part of the system that's really critical for management. If your system's down here, on the bottom of the base, you've got nothing to worry about. It's when it's here, perched on the edge of some threshold, you really need to know how far is it going to go before it's gone. And what are the likely consequences of it going? And then what do you need to do to bring it back? So management of thresholds in social ecological systems is concerned with identifying and modeling these thresholds of potential concern. Let's go back. Oops. Okay. So this would represent a threshold of potential concern to the system. You identify those. And then once you've identified those thresholds of potential concern, then you develop the models which can be tested through adaptive management, as I've said. And one of the interesting things, although it might look very technical, those models are a bit of a handful or a headful to understand. A good resilience thinker or resilience coach is a good facilitator can generally work with a rural group and come up with a model of thresholds of potential concern within 2 to 3 days. I have a colleague in Australia who's doing these things on a large scale now because the Australian government has made it mandatory for all catchment management authorities to produce a resilience assessment before they apply to government for money to manage their catchments. So he's done about 200 of these now. And to get to a model of thresholds of potential concern is a relatively easy thing. Beyond that, then you need models to work with you to develop a model which contains the actual measurements and predictions and the assumptions and all the things that decision makers and government bureaucracies like to understand and work with before they decide yes or no. But at a rural level, with switched-on farmers, they know an awful lot about what happens with their system. And as I said earlier, they tend to be intuitive managers, pattern managers, and with a model like this, and this is something that's yet to be demonstrated by application, but I think they will very quickly make use of a model like this and apply it without going to the extremes of the mathematical model, but more sophisticated users might require. But to get to that model, you need to understand how these core resilience models work and then go through the process. Well, the whole purpose of this really boils down to these two strategic choices. Maintaining the system within its current state, and that's to enhance its ability to bounce back. Okay, so that's the bounce back side of it. And then the alternative is deliberately engineered transformation, taking it across a new threshold, bounce forward. So you do your assessment, figure out your thresholds of potential concern, and then you make a choice. Do I want to keep the system in its existing state, or do I want to change it?
Could you give us a practical example of that?
Yeah, here's one. This is an assessment done in the farming district in Australia. Each one of these boxes represents a threshold of potential concern, and the arrows show the interlinkages between them. One of the really interesting things to notice is these are thresholds in the social domain, and they operate right across all the scales, from farm to catchment to state and nation. And then if you follow this arrow down, you can see how they affect all of these things. So what this model is telling you is how human values in that part of Australia and the laws and policies that have arisen as a result of those values have led to all these potential problems in the Australian environment in this particular area. And then it goes on to show you thresholds of potential concern in the biophysical soil acidity, which we talked about earlier, and then how that affects farm financial viability, and then the size of the dairy and fruit processing sectors. So those are the industries that are dependent on the farm, and how all that then goes back up to affect these. And then these are hit down here on the right-hand side, the kinds of shocks that they anticipate are going to push some of these thresholds over into some kind of alternate stable state. So this particular farming community recognizes that they're in a pretty undesirable place, or at least parts of it are in an undesirable place, and they're working deliberately now to try and transform the kinds of things they produce from the land, the kinds of things they do to manage the land. You can carry away a copy of this presentation, so you don't have to worry too much about getting it all down. And it's fully referenced, so you can go back to the literature and look it all up. Okay, so this is this Goulburn-Broken example illustrating the strong influence of social values. Links between the threshold indicate the cross of one may cause other thresholds to cross, so you get these cascades of change across systems. Talked about the soil salinity problem. Transformation and change of some parts of the system is essential, and that's exactly what they're doing now. And then in other parts of the system, general resilience can be enhanced with minor adjustments in management practice. We'll come on to general resilience in a minute. Okay, so that's how it works. That's how the figure of 8 and the ball and basin and the panicky, how they all eventually boil down to a very simple model of threshold of potential concern in a social ecological system, giving the manager of that system the opportunity to think really hard about, do we want to continue doing what we're doing, or do we want to change the way we're doing it? And that's the essence of resilience assessment. It's the essence of resilience-based stewardship of the land. So, questions?
Have some where you want some.
Sorry?
Have some where you want some.
Yes, are there any?
Are there any questions?
top of your last slide, you have an example. You wouldn't mind just, yeah, no, one more forward.
Forward?
Yeah.
Forward.
Yeah, well, influence of social values on landscape, and there's some good examples of the reverse, where the landscape is undergoing change and that affects value systems. So it's basically, causing, I suppose, a collapse of value systems and reorganization of those.
You say you have an example?
No, I'm asking you if you have.
There is an example from a large river system in Hungary, which was managed in the sort of fairly typical style of most rivers. It was dammed and levied and was subject to periodic flooding and the system breaking down. And there, a group of farmers got together and said, no, we used to do it in a much better way in the past, let's go back to traditional farming methods. And over a period of time, they actually convinced government to change policy for the management of that river. And they've gone back to a traditional system of river and floodplain and agricultural management.
Yeah, I just wanted to be clear. So if we're talking about thresholds of potential concern for maybe a community adaptation scenario, you things like savings, adequate savings, sort of maybe ability to work together to resolve problems, that might be an area that's important. Or access to sort of improve seeds to deal with drought or to deal with flooding, things like that. Are those the types of things that come out of that assessment?
Most of what you're talking about there, I think, is potential for change. It sounds as, the way you're describing it, it sounds as though potential for change might be being eroded, which would tend to make your system more vulnerable to shock, to change. When a system crosses a threshold, there is some fairly fundamental reorganization of the elements of the system. Some elements drop out, new elements come in, and there's also a fundamental change in the relationships between the elements.
How do you rule out subjectivity in setting those thresholds? Surely that's the
You don't.
that's the maturity of the model is measuring looking at resilience. But if you're applying a level of subjectivities to those thresholds of potential concern, surely you should be allowing it a little bit more flex.
That's why you develop the model and then apply it adaptively, because the model that you develop is full of assumptions because of all the unknowns. The more knowledge that you can bring to bear on an understanding of the problem, with luck, the less assumptions you'll have in it. But however good the knowledge is, I don't think you're going to come up with a really accurate model. That's one problem. The other problem is that the larger environment within which your system operates, that's also changing. So you apply it adaptively to test the assumptions in the model, and also bearing in mind that the system is going to change around you, the larger system within which you operate. So what seems like a good idea today may in 100 years' time be a very bad idea because the larger environment has changed significantly.
How do you identify the threshold?
Well, in the first instance, you base it on whatever knowledge that you might have. In some cases, thresholds are quite well known. In other cases, they're just suspected. That's an identification of thresholds and understanding their behavior. That's one of the primary aims of resilient science, because science is all about better knowledge that you can apply to these systems. But for a lot of them, you just have to go with what people who live on the ground know and understand. And you say, well, I've observed, somebody might say, well, I've observed this kind of change over the last 50 years or whatever it is. I think it's leading to this kind of situation which is undesirable. For me, that's a threshold of potential concern. And you get a group of stakeholders in the room, and by and large they've got a fairly good idea of where the thresholds are. The things that they want to avoid happening if possible.
I'm just wondering how this applies to certain things like genetic organisms. That you're changing to different thresholds based on control.
Yeah.
But then it unlocks all of these other unknowns.
Yeah, whatever.
Um,
Yeah, GMOs.
I'm trying to
Changing the genetic composition, changing the genetic properties of plants. Plants are small, fast variables. The genetic code is even smaller and faster.